Hello, my name is Gabriel, and in this video I'm going to explain my data analysis for the Smoky Mountain Data Challenge in 2017. In particular, I use the Neutron Diffraction data. So let's look at this data. This is what the data looks like. So for different values of temperatures, we have different curves of intensity as a function of typical distance in the material. And we can see that the different spikes here, there are many peaks in this data. So the idea of this data challenge is that we find all these peaks, we characterize them, and we decide if a phase transition happened or not in the material. So what I did is, first let's learn how to characterize the peak. In particular, we're looking at the peak around 3.25 angstroms as suggested by the instructions. So what I do is I look, so this is the peak around 325 for temperature equals 23 Kelvin, and for 151 Kelvin, as we're gonna see, this is an interesting temperature where the peak structure changes drastically. So this, let's say it's a normal away from the phase transition temperature intensity curve. This one is close to a phase transition, so it looks very different. So what I decided to do is I fit a Gaussian curve with plus a background in this peak, in this curve, and these blue points here are the residues after the fit. And with the fit here, I get these values back, right? I have the area under the curve, the mean is of the Gaussian is just the center of this peak, and the width of the Gaussian is a characteristic width that I use to identify these peaks, to characterize the peaks. And we can see here for different values of temperature how this fit changes. In particular, again, close to the phase transition, we see that the fit is terrible. We can look at the residues or the chi-square here. But that's fine because we're not actually interested in these values per se, in the values of the mean or the characteristic width. We just want to find a phase transition. So even though the fit, it doesn't describe the shape of this peak here, we're not interested in this shape in particular. We're just interested in a number that would detect a phase transition for us. And we can see that that happens here, right? Because the width, for example, the sigma of the Gaussian gets much larger here compared to other temperatures away from the phase transition. So we can see here that this is like almost 5 times larger, the width here, than compared to here. So if we do this for all temperatures, if I characterize the 3.25 peaks for all temperatures, this is the area under the Gaussian of that peak for all the different temperatures. This is the mean and this is the width. So we can clearly see that around this interesting temperature there's something funny going on, where the fit, as we saw, it fails because the peak is not Gaussian at all. But then we can detect that by looking at these quantities right here. So if we plot them at the same plot, the same scale, just to have an idea, we can clearly see that around this temperature of 150 Kelvin, something changes, right? So everything becomes different for the mean, the width, and the area. So what I decided to do is, well, first we have to learn how to detect all the peaks in a curve. So I use this algorithm here. It's a MATLAB based algorithm. So I just changed it to Python, and see, actually this guy in this reference changed to Python, and I just simplified the algorithm a little bit because this is more than we need for this data set. So basically the idea here is that all the points in the data set are peaks, and then you start removing the some after a few criteria. So basically I just use 2 criteria. The height of the peak has to be bigger than a certain threshold, otherwise I treat it as background. Background would be this one here around 100 in this intensity curve, for instance. And the distance between 2 peaks has to be, in my case here I chose 65, but anyway, you just optimize. For instance, we can see a little peak here, but we are more interested in this higher peak here. So by choosing this distance between the peaks, I stop finding this peak and I only find the big peak here that is more interesting for our analysis. So given that now we know how to find all the peaks and we know how to characterize them by doing that Gaussian fit and getting the values back, we are ready to build a pipeline here and actually find all the phase transitions, or actually find if a phase transition happened between the temperature or not. So for example, these plots right here, they show for all the temperatures from I think we have 140 temperatures in our data set. For all these temperatures, I run that pipeline where I find all the peaks in the data set and I characterize them by the Gaussian fit. And this is, for instance, the difference between the number of peaks between for all the different temperatures. So I look at some temperature, the adjacent temperature T+1, and I look at the difference between the number of peaks. So we see that for all of them, it's between 0 and 1, or -1 of course, but absolute value. But then around that temperature here of 150, we have a case where the number of peaks changed a lot. And also we have this outlier here in the end, but this last data point always has a funky mean and a funky width and stuff, so I'm not paying attention to this data point right here. I actually have to understand better what's going on over there. And this is, for instance, given that two temperatures, they have the same number of peaks, this is the difference between the center of all the peaks. So we can see that there's something very interesting happening here also, where the center of the peaks, they move a lot, but it's still not that close to our interesting region where the phase transition is obvious and occurs around 150 Kelvin. So this is the way that I started looking at these things, how to define the phase transition, and in the end, I think I defined as a certain number of the difference between the number of peaks between two temperatures and the difference between the mean width of all the peaks in that particular temperature. So if it satisfies a certain criteria, I say that a phase transition occurred for that temperature. So yes, I'll explain things further in the poster for the Smoky Mountain conference, and I hope we can talk more about that. Thanks.